In a previous video before this video, we outlined the sequence of steps to follow in order to construct a confidence interval for the difference of two proportions. But, as we recall, in the world of inferential statistics, to answer a research question, we can follow one or both of two major paths, namely the method of confidence interval or hypothesis testing. So that gives us the basis to explore how to conduct hypothesis tests on the difference of two proportions. How do we go about doing this? Here is an example. A 30-year study was conducted with nearly 90,000 female participants. During a 5-year screening period, each woman was randomized to one of two groups. In the first group, we had women who received regular mammograms to screen for breast cancer. And in the second group, women received non-mammogram breast cancer exams. No intervention was made during the following 25 years of the study, and our goal is to consider death resulting from breast cancer over the full 30-year period. Results from the study are summarized in the table below. So in this table, what we have is that a total of 44,925 received mammogram tests, whereas a total of 44,910 received non-mammogram tests. And so they are classified as being in the non-mammogram group. So here's an initial consideration for you. If mammograms are much more effective than non-mammogram breast cancer exams, what do you think? Do we expect to see additional deaths from breast cancer in the control group or in the mammogram group? Or, on the other hand, if mammograms are not as effective as regular breast cancer exams for early detection, we would probably expect to see an increase in breast cancer death in the mammogram group. Well, let's use a significance level of 0.05 to conduct the appropriate hypothesis test. Our first point of stop is what is the outcome variable that we're keeping track of. In this case, we're interested in the instance or the incidences of deaths in both groups. So the outcome variable is the death rate. Next, how do we set up the null and the alternative hypothesis in this case? We're interested in first in the mammogram group. What is the proportion of deaths in the whole population of those who received mammogram tests compared to the proportion of deaths in those who are in the control group? Are they the same or are they different from each other? So this is the null hypothesis versus the alternative. And take note that based on algebra, if I have PM equals PC, if I subtracted PC from both sides, the proportion of deaths in the control group, I would have on the left-hand side PM minus PC, whereas since I have the same quantity on the right, I will have 0 on the right-hand side. And the alternative then will be equivalent to saying the difference between these two groups is not nothing. If it is not nothing, then it is significant of that it should command some attention. So having set up the null and the alternative hypothesis, the next step is to calculate the pooled proportion. You see, whenever we are computing or whenever we are carrying out a hypothesis test for difference between proportions in two groups, and the null hypothesis is the hypothesis of no difference in the outcome variable between the two groups, we must always compute a quantity known as the pooled proportion. The pooled proportion comes from pooling together both samples and computing the proportion of the outcome variable in both groups. To break this further, to simplify this further, the total group here is, we have out of 44,925 plus 44,910, how many deaths did we experience in both groups pooled together? That will be 500 plus 525, and that will give us 0.0111 approximately. You see, this pooled proportion will be carried over into conducting the model check. And the model check requires us to answer the question, is it reasonable to model the difference in proportions using a normal distribution? To do that, the first thing to check is the condition of independence. The condition of independence is guaranteed if the patients or the experimental units in the study were randomized into the mammogram group and the control group. Well, we're told here, based on the context here, that the patients were randomized into one of two groups. So that tells us that this condition of independence is satisfied. Next, we're going to go to each of the two groups, the mammogram group and the non-mammogram group. We're going to use the value of the pooled proportion to multiply the number of those in the mammogram group. And remember, the total number in the mammogram group is 44,925. So that value, I'm going to bring it down here. So I have 44,925 multiplied by the pooled proportion. That'll give 498.6675, which we like that it is greater than 10. In addition, similarly, we look at the same 44925 minus the complement of the pooled proportion. That is 1 minus the pooled value. The pooled value is this value, so 1 minus that value multiplied by the number in that subgroup, that is 44,925. And we have 44,426.3325, which is also greater than 10. Both are greater than 10. Then we step over to the non-mammogram group or the control group. And we look at the number in that subsample, that is 44,910. So you have 44,910 multiplied by the pooled proportion. You have 498.501, also greater than 10. And similarly, we have 44910, the number in the control group, multiplied by 1 minus the pooled proportion. That will give 44,411.499, which is also greater than 10. The fact that all of this success failure counts in the two groups are greater than 10 guarantees that we can use the normal distribution to model the difference in the proportions. With that said, we are ready to compute the point estimate. The point estimate will be what in the sample, what is the proportion of deaths in the two groups? Well, if we go back to the table given, the proportion of deaths in the mammogram group is 500 out of 44,925, whereas in the control group, it is 505 out of 44,910. So I'm going to look at that difference. In the mammogram group, we have 500 out of 44,925 compared with those in the control group, that is 505 out of 44,910. That would give us 0.01113 minus 0.01124. And that will give us approximately negative 0.00012. Well, with that done, let us see if we can use StatCrunch to compute all the necessary values that I have in these pictures here. Take note, this value is already given here. We can do it in StatCrunch. Let's do that. So I'm going to go over, pull over StatCrunch. And in this case, I'm going to X out of this, go to statistics, go to proportion statistics. Next, go to ToSample, and then with summary. It is going to prompt you to key in some values. In the first sample, what is the proportion of successes or the proportion of event or outcome variable of interest? In this case, that's the number of deaths. So we want to see 500 out of 44925, out of 44925. And in the second group, it was 505 deaths out of 44910. And our interest is to conduct a hypothesis test for the difference in proportions. So in this case, that is equivalent to the difference being 0 right here to not being 0. And our interest next is at what level of confidence are we carrying out this test? We have a 0.05 level of significance. So we can set that up here in the significance value. And you already have that here, so I don't need to alter that. I'd like to show the critical value and compute. So here are the output values here. You will notice that the sample difference here is what we got from is equivalent to the value we got from our AND calculations right here. So with that said, we also have in addition the p value that we seek. So we're going to take that p value to work. So our conclusion is as follows. The p value here, the probability value, is 0.8698, and the alpha value that we have conducted this at is the level of significance, which is 0.05. You have 0.05. You'll notice that the p-value is definitely greater than your alpha. Recall the decision rule. When your p-value is greater than alpha, we fail to reject the null hypothesis. And if we're failing to reject the null hypothesis, that means the null hypothesis is the one who won this battle. And that means we do not have sufficient evidence for our research or test hypothesis, namely the alternative hypothesis. So we therefore conclude that we do not have sufficient evidence in favor of the alternative hypothesis that we wanted to test. This means that mammograms do not make any difference. That is, since the proportion of deaths in the mammogram group and the proportion of deaths in the control group seem to not be different from each other, they're about the same. It means that taking a mammogram test does not really make any difference, either reducing or increasing the proportional rates of breast cancer deaths. And this study we've just considered and the data collected, does it represent an observational or an experimental study? As you might recall from lesson 1 or from unit 1, this data set required randomizing patients into two groups and assigning treatments to them. This is a characteristic feature of an experiment. So, considering the randomization of patients into groups, this is an experimental study. And for an experimental study, remember, a level of causation conclusion could be reached provided all the principles of a good experimental design are met. With that example, let's consider yet another one, similar in a different context. Suppose as part of a national study of economic competitiveness, a marketing research firm randomly sampled 200 adults between the ages of 25 and 35 living in metropolitan Seattle and 180 adults between the ages of 27 and 35 living in metropolitan Minneapolis. Each adult selected in the sample was asked, among other things, whether he or she had a college degree. From the Seattle sample, 66 answered yes. Let's take note of that. And in the Minneapolis sample, 63 answered yes out of 180. And in the other group, it was 66 out of 200 in the Seattle sample. Based on the sample data, can we conclude that there is a difference between the population proportions of adults between the ages of 27 and 35 in the two cities with college degrees? We are to use a level of significance of 0.01 to conduct the appropriate hypothesis test. Well, in this context, the outcome variable of interest would be an adult who holds a college degree in any of the two cities. So the appropriate hypothesis to set is to go to the Seattle sample and look at the proportion of those who hold a college degree in Seattle compared to the proportion of those who hold a college degree in Minneapolis. Might they be equal, or versus the alternative that they are not equal? Similar to the last example, this is equivalent to setting your null hypothesis as saying the difference in the proportion of adult college degree holding adults between the two cities is nothing, versus the difference between the proportions is not nothing or something significant. So the next step would be to calculate the pooled proportion, which means we'll pool together the two groups. We pooled 200 adults from Seattle plus 180 from Minneapolis, and from both groups we have 66 plus 63. That would be equal to 9 and 129 out of what? Out of 380. That will give us 0.3395. This is the pooled proportion that will be what taken forward to do some model check. All right, from the pooled proportion, we'll set that aside for a little bit. The first step to check, or the first condition to check under the model check, is the independence check. And we notice that since the participants rather, were randomly sampled from different cities, that checks out what the condition of independence of data values. Then secondly, we go to the Seattle sample. How many people were in the Seattle sample? There were 200 of them, multiplied by the pooled proportion. That will give a value equal to 67.9, which is greater than 10. We like that. Then again, 200, the same number in the Seattle sample, multiplied by 1 minus 0.3395, that'll give 132.1, which is also greater than 10. We check that off. Then in the Minneapolis sample, we have 180 multiplied by the pooled proportion, you have 61.11, which is also greater than 10. And lastly, 180 multiplied by the complement of the pooled proportion, you have 118.89, also greater than 10. With all of this checking out, we can say that using the normal distribution to model the difference in proportions is reasonable. With those conditions checking out, we would like to look at the point estimate of that difference based on sample data. So going back to the sample, what was the proportion of adults in the Seattle sample who hold a college degree? There was 66 out of 200, compared to those in the Minneapolis group, that was 63 out of 180. With our computations, we should get approximately negative 0.02. This can be gotten in StatCrunch along with other values we need, which is the p-value. So let's do that in StatCrunch. I'm going to go here and X out of this, and I'm going to go to Stats, Proportion Statistics, to Sample, with summary. In the Seattle group, it was 66 out of 200. In the Minneapolis group, it was 63 out of 180. And we want hypothesis test for the difference, either equal to 0 or not equal to 0. And let's see, what level of significance are we using? 0.01. So I'm going to change this. I'm going to click on critical value and also change this to 0.01 and click on compute. And so I will have this result, which I've copied onto our notes. So let's look at what that result tells us. We have the p-value, which is 0.681, and the alpha, which is 0.01. And I'd like to note that this is greater than 0.01. When that happens, again, we fail to reject the null hypothesis, which means, again, the null hypothesis won in this case. And we do not have enough evidence for the alternative. So that means we do not have sufficient evidence in favor of the alternative. The alternative was saying that the difference is not subject to chance, that it is statistically significant, whereas the null hypothesis is saying that the difference is nothing, it's not a big deal. So this means that the sample data collected and analyzed does not provide strong enough evidence to say that there is a significant difference in the proportion of college degree holding adults in the two cities. Now, because this was an experimental study or an observational study, let's go back to the question, to the scenario. Notice that adults were randomly sampled. There was no conditioning of any adults to get a college degree or not. So there was no effort on the part of the researchers to intervene by forcing anybody to go to college. So in this case, this is just an observational study. They observed data that was already existing there and analyzed it. So this is a case of an observational study. Based on what we learned in Unit 1, you cannot reach any causal conclusions. The best we can reach is an association conclusion when we're dealing with observational studies. This is just to bring back the ideas of what we learned in Module 1 into this context.